Hi, everybody. This is Professor Monty, and we are going to jump into section 2.2. If you looked at my last video, 2.1, we were just doing a review on the algebra of both exponential and logarithmic functions. Today, we actually get to start going into the calculus aspect of that. Now, let's talk about exponential functions real quick. Recall, if we look at the function f of x or y equals e to the x, the function we graphed it looks something like this. Now, there's something very, very special about the exponential function. Now, when we have e to the x, we call that the exponential function. Other functions that have exponents up in the, with variable up in the exponent, 2 to the x, 3 to the x, things like that, those are called exponential functions. But if they refer to the exponential function, they're specifically talking about e to the x. And here's what's really special about that. If we look at any point on the curve, say right here at x equals 0, and we look at the tangent line right there, remember the derivative is the slope of the tangent line. What's special about there? Let's put a little chart here. We're going to have x, we're going to have e to the x, and we're going to have the derivative of e to the x. And what we're going to find out, if x equals 0, what we get right there, well, e to the 0, remember, is just 1. The derivative, and remember the derivative is the slope of the tangent line. If I look at the slope of that tangent line right there, it's in fact a slope of 1. So the derivative happens to be exactly the same as e to the x itself. And let's go ahead and erase a piece of this so that it doesn't get in our way. And let's go back to the graph. If I go over to x is 1 and I look at the tangent line right there, it looks about like that. At 1, now this is going to be e to the 1, which is about 2.7. But the derivative is also exactly e to the 1. Again, approximately 2.7. And that works for any x value I get. This would be e squared. The derivative is e squared. So in fact, what happens is the derivative of e to the x is just e to the x. That actually is the entire section. We could stop right there and say, look, that is the section. That's what's happening here. What's really interesting about this, e to the x, the exponential, is the only function other than 0 whose derivative is the same as the original function. Now, we also have to remember the chain rule, and I'm going to write that right here. Remember the chain rule. Now, in just e to the x, there's no chain rule because the exponent x isn't a composed function, but here's what they would call the extended derivative of the exponential. So if I'm say taking the derivative of e to some function, I get back exactly e to that function, but then times the derivative of whatever the exponent was, because that was my composed function. That's the chain rule. And so now we could really say, hey, that is the entirety of this section, because it really is. All I'm going to do from there is we're going to look at some examples. So if that didn't really set well with you, if you don't like that ddx notation, think about this. If I have f of x is e to the x, the derivative, f prime of x, is also just e to the x. That's what I was saying in that first one, where the derivative of e to the x is just e to the x. That's another way of saying it. If Newton's notation makes more sense to you, that's all we're saying there. Okay, but let's actually go into the book. We'll look at some examples so you see how this works. First problem I picked out is problem number 2. And on all these problems, they just say differentiate. I'll just put differentiate up here. And that's all we're doing at this point is finding derivatives. So number 2 says g of x is equal to e to the 3x. Well, differentiate, of course, means find the derivative. So I'm going to find the derivative. Remember, if I go back to that second box that I had, let me show you real quickly. We get back the original exponential we started with. Whatever we started with, when we take the derivative, we get exactly that back, but then times whatever the derivative is. So let me erase those so when we're looking back at our notes, that doesn't confuse us. So when we take the derivative, I get back e to the 3x, exactly what I started with. But it's not just e to the x, it's a 3x. That's a composed function. That 3x is the function inside the e to the x function. So then I have to say times 3 from the chain rule. And that piece right there was my derivative of the 3x. That's where that piece came from. And so usually we write it just as 3 e to the 3x. And so it comes out real quickly. It's a little bit different than it started because the chain rule gave us that multiplied by 3. Let's look at some more examples. Here's problem 4. Capital G of x, they say is 2 e to the 4x. Well, if I take the derivative, g prime of x, I get all that back, 2 e to the 4x. But then I say times, sorry about that, I say times 4 from the chain rule because, again, that was the derivative of the 4x. And so I'd usually multiply the 2 and the 4 together, and I get 8 e to the 4x. And that's my derivative. Notice these work completely different than power functions. If I have a power function, say x to the 5th, the derivative is going to be 5x to the 4th. The exponent drops by 1. The exponent with an exponential function it's not reduced by 1. It stays the same as it was before. So that comes up kind of in this next problem. Here's number 6. We'll lift that up so hopefully I don't get the keyboard again. F of x equals x to the 5th minus 2 e to the 6x. Remember, we get to take the derivative of each of these separately because it's separated by a subtraction. The derivative of a difference is just the difference of the two derivatives. Now I've got x to the 5th. That's a power function. The derivative of x to the 5th, just as we've done before, that's 5x to the 4th. Bring the exponent down, drop the exponent by 1. But e to the 6x, we're not going to drop that by 1. We get back all that 2e to the 6x. But then times 6 for the chain rule. Again, remember that was the derivative with respect to x of the 6x. That's where that 6 came from. And so now I can multiply that 6 times the 2. Notice it's not times the whole thing. I'm not going to distribute the 6 in, just the 6 times the 2. So I still only get 5x to the 4th, but then minus 12 e to the 6x. I like this problem because it shows us with a power function, that first one, x to the 5th, I just take the derivative like I usually do using the power rule. But with the exponential, it's a different rule. I get back the entire exponential and then just times whatever the chain rule gives us. All right, so here's problem 8. F of x equals x to the 7th times e to the 4x. Now, on this problem, notice it looks fairly simple, but there's really multiplication right there. There's x's in both pieces. We have to use the product rule. So now, this is why we use that product rule. When we first learn the product rule, oftentimes we can just multiply things out and then take the derivative, make it a lot easier. When we got into the chain rule, we could make it so we couldn't really multiply out things nicely, But here on problem 8, we can't simplify that whatsoever. This, we have to use the product rule. There's absolutely no choice. And remember, the product rule, first times the derivative of the second plus the second times the derivative of the first. And so in this case, we're thinking about f of x is the x to the 7th, and g of x is equal to e to the 4x. So that's what I'm doing. I'm using that in that way. So now when I go f prime of x, it's the first, x to the 7th, times the derivative of the second, e to the 4x times 4 from the chain rule, plus the second, e to the 4x, times the derivative of the first, 7x to the 6th. So again, first times the derivative of the second, plus the second times the derivative of the first. And now usually what they're going to do is they're going to factor that out. Notice there's an e to the 4x in both of them. There's also an x to the 6th. So I can factor out that x to the 6th and the e to the 4x. What it's going to leave me with, there's still a 4 and another x in that first piece. And in the second piece, all that's left is the 7. So I just say plus 7. And there's my derivative. So again, I'm just factoring out the greatest common factor there. Okay, let's try another one of these. This time, well, you'll see what it is as soon as I write it down. G of x equals e to the 3x, but with the numerator of x to the 6th. Again, a very simple looking problem, but I have to use the quotient rule. And remember, the way I like to say the quotient rule, remember how it goes? It's low d high minus high d low, square the bottom, and away we go. So of course, this is the high, this is the low. And that low d high means the derivative of the high, and then the high d low, derivative of low. So g prime of x, so let's go in steps, low d high, e to the 3x times 3 from the chain rule, minus high, e to the 3x, no chain rule now because I'm not taking the derivative, it's just a high, but then times the derivative of the low, 6x to the 5th. All over the bottom, squared. All right, so again, we're going to factor this. Let me show you what the steps were. So this was high, d low, minus, I just backwards, low d high, minus high d low, square the bottom, and away we go. All right, so let's see. What's common on top? We've got an x to the 5th and an e to the 3x. So I can factor out that x to the 5th and the e to the 3x. And let's see, there's still a 3 and an x left in that first piece. And in the second piece, just the 6. Oh, I could have factored out the 3 also. Let's pull that 3 out here as well. Erase that 3. So I factored out a 3. So in that first piece, since I factored out the 3 and the e to the 3x and the x to the 5th, there's still one x left in there. And then in the second piece, I factored out the e to the 3x. From the 6, I factored out a 3, left me at 2. And then I factored out the x to the 5th, so it's just x minus 2. And then it's all over. Remember, on the bottom of power to a power, we multiply the exponents. And now we can even go one step further, because 5 of these x's cancel 5 of these and leave me with 7. Subtract the exponents in that case. So then my answer, g prime of x, is 3e to the 3x times x minus 2 all divided by x to the 7th. And there's my answer, fully factored out and simplified. So do practice those, make sure you can kind of get those figured out. And then all I have left, I have a couple problems, word problems, a couple applications to see how this applies to things. And then you'll just need to practice these. And I think you'll get those figured out nicely. All right, but here's the first problem I wanted to show you. It's problem 49, growth of a retirement fund. Maria invests $20,000 in an IRA account whose value after T years is modeled by V of T, the value after T years, is 20,000 e to the 0.0545 T. Let me tell you a couple things about that. That 20,000, that's the starting amount in the account. And that 0.0545 up in the exponent, that's the growth rate. So she's starting with $20,000 and it's growing. This is the formula for continuous compound interest. It's growing at 5.45% per year. So that's the idea. It says use the model to estimate the value of Maria's IRA or IRA account after 7 years. Well, so part A, that's just the value after 7 years. I just plug it in. So it's 20,000 e to the 0.0545 times, and then T is 7. Now, if you have to, some of you have to put a parentheses here to make sure you get the right answer. Otherwise, it's just going to do e to the power and then multiply the whole thing by 7. So make sure that you can get this answer correct. If it shows you when you plug it into the calculator, actually going into an exponent, then you don't need to put the parentheses there. But if it doesn't, you have to. So let's see, 0.0545 times 7. I get, the account has gone from $20,000 to $29,000, 289, oops, 289. And since it's money, I'll go to 2 decimal places. It's 593, so we'll just round to 59. So that's the total amount in the account after 7 years. Here, we'll even write this. Total amount in IRA after 7 years. So that's what that represents. Let's get that 7 down a little bit so we can actually see it. That just didn't really help a lot, did it? That's better. Okay. Part B says, what is the rate of change in the value of the IRA account at the end of 7 years? Well, rate of change, remember, that's derivative. So we have to take the derivative. I'm going to erase that so if you're looking back at the tape, it doesn't confuse you when you're looking at part A. So for part B, we need the derivative. Well, the prime of t, remember, constant multiple, the 20,000 stays there. We get back the entire exponential, e to the 0.0545 t, but then times from the chain rule, the derivative of the exponent. Well, the derivative of the exponent, if the t goes away, I just get the 0.0545. I can multiply that by the 20,000. I don't want to yet and then round it off. I'm just going to leave it there when I plug in to find my v prime of 7. Don't round before your final answer. So it's going to be that times 7. That's going to be my exponent, but then times the 0.0545. So you're welcome to multiply that 0.0545 times the 20,000. But if it doesn't come out nice, if there's a decimal that keeps going, don't round it until you multiply it by the e to that power, or else you'll have rounding errors. So I'm just putting it in the way I see it. I'm going 20,000 e raised to the power 0.0545 times 7. Notice that's actually everything that I had from the previous problem. And then times 0.0545. And think about what's happening, and let me show you. The answer I get, again, rounded to 2 decimal places for the nearest penny, 1,596.28. So 28 cents. Now, think of what's happening here. This piece here was all the same that I had before. What that represented was the total amount in the account after 7 years times the interest rate for 1 year. So the number that I got, that's my predicted interest in the next year, which would be year 7, because we're already at 7 years. So this is predicted interest for year 7. Oops, for year 8, the next year. And notice we can only use it for the next year. We can't use it for year 12 because we're going to be basing it, the interest, on a higher amount that's in the account at that time. So the derivative only really is useful predicting for the very next one, unless you just have a linear equation and it goes up at the same rate all the time. All right, so that's the idea. That's the end of that problem. I kind of liked it because we get to see both what the amount means and what the derivative means. And we see that the derivative makes sense what it represents because it was the exact same function we had in part A times the interest rate. All right, let's do another application. And let's see, we'll post it about right there, but let me go grab it real quickly. It is in here, and it's problem 58. So let me copy that, and we'll paste it in right about there. All right, so 58, memory retention. A student memorized 120 vocabulary words for his Gaelic exam. After T days, the number of words W that he retained is given by, and they give us the formula. And it asks us a few things. Find the number of words he retained after 4, 10, and 20 days. And then we'll get to the next parts. But for part A, so we've got T and we've got W of T. So the number of words that he still has retained after a certain amount of days. And they ask us for a couple of these. Let's see, this W of T, we'll write out what the formula is. 35 plus 85e to the negative 0.08 t. Go ahead and extend that all the way over. So the t's, he says, after 4 days, after 10 days, and after 20 days. So I'm just using my calculator. I'm putting those values of t in where it goes. So I've got 35 plus 85e raised to the negative 0.08 times 4 for the first one. Now notice this formula is very similar to what we had in the last problem. That e to the negative 0.08 t, that means the negative, he's losing words at a rate of 8% per day. So I plug in 4. Now I'm going to round this to the nearest whole number. I get 96.7, so we'll say about 97 words. And they're all going to be in words. If I do the same thing and I plug in a 10, now he's down to about 73 words. And if I plug in a 20, he's down to about 52 words. And this is where they talk about use it or lose it. If he's not practicing his Gaelic, and I would imagine that you don't have a lot of opportunity for that in most places, you lose it fairly quickly. So let's see. So it went from 97 down to 73, down to 52. B says find the limit of the number of words he knows as t goes to infinity. So let's look at part B. Limit as t goes to infinity. Now let's write down the formula. Instead of writing W of t, we'll write down the 35 plus 85 e to the negative 0.08t. So that's the question. But one thing I want to point out, that negative exponent, notice that flips over and makes a denominator out of the e to the 0.08t. So it's really this. Limit as t goes to infinity. I don't know why I made the t so big. So we'll make it a little smaller. Limit as t goes to infinity of 35 plus 85 divided by e to the 0.08t. Remember, that's what that negative exponent did. Now, remember that denominator, e to the 0.08t, that's e, 2.7, but everything's increasing by 8% per day. So it's increasing. So the denominator is getting bigger and bigger. Well, as the denominator gets bigger, the fraction, the numerator is not changing. So the fraction gets smaller and smaller. As t goes to infinity, this whole piece here goes to 0. And if you want to do a little chart out to the side where you do t getting bigger and bigger and see what happens to 85 divided by e to the 0.08t, go ahead and do that. And you'll see that that goes to 0. But we've seen that in other lectures, so I'm not going to use the time to do that. But then notice all you have left is the 35. And there's no t there, so it doesn't matter what t's doing. 35 stays 35, and that's actually my limit. So we're going to get down to the point where the student has still memorized 35 words. The student says he started at 120 words. He'll lose all of them except 35. And then he'll remember the 35 forever, is what this model is suggesting. All right, so let's think about what's happening. I kind of like, see, it says use a calculator to graph this. I wouldn't make you graph this, but let's go to the calculator and see actually what this looks like as a graph. I've got a graphing calculator, so I'll refer to that. I'll show you how to put that in real quickly. All right, so let's take a look. And notice it says use a calculator to graph W from 0 to 30. Remember, we started at 120 words, and then the words are going down. So what I'm going to do is I'm going to change my window to account for that. So let's see. We'll go up to 125, and we'll do 0 to 30. So let's do this. Here's my calculator. So I'm going to plug in y equals, I'm going to plug in the formula. 35 plus 85 e raised to the power. And notice on mine, it gives you the power, so I don't need the parentheses. If yours just says e and then the little caret that looks like this, little upside down v, but it's not up in the exponent, you do need to use parentheses or it's not going to work correctly. Remember, that's this down here is the negative sign. This one over here is subtraction. I don't want to use that. I'd get an error. So negative 0.08, and then times, they use this as the variable key. So there's my formula. I'm going to graph it, and notice if I hit graph, I don't see anything, and it's not where it wants it to be. So what I'm going to do is I'm going to go change my window. And it says graph from 0 to 30. So my minimum will be 0. My maximum will be 30. I'll leave my scale at 1. And for my y values, I'm going to start at 0. We'll say they remember 0 words all the way up to, we started at 120. I'll go 125 just so that we're not at the maximum. And then now when I go to graph it, it'll actually show me the graph. So at 0 days, he had remembered 120 words. It starts to go down, but notice it's going down at a less and less of a rate. starts as a fairly rapid decrease in words, but then gets less and less. And in fact, it makes sense it gets less because it's going to have a limit, remember, down all the way at 35. So once we get past a certain point, this is not going to get below 35 words because that was the limit. Notice a couple things. It's decreasing, first derivative is negative, but it's decreasing at a lower and lower rate. So the second derivative is also negative. That's why it's concave up. All right, so I said that backwards, didn't I? We know the first derivative is negative because it's going down. The second derivative is positive because it's concave up. The slopes are getting bigger from a positive perspective because say this was -1, now it's -1/2, -1/4. So the second derivative is positive is why it's concave up. Apologize for that. Okay, so one more part on this problem that we'll look at. So let's go back up here. So we saw the graph. We can kind of sketch that if we want to. I don't think I'm going to. Maybe we should in case anybody just has these notes. So let's see. The graph looked like this. This down here would have had a horizontal asymptote at 35. It started up here. This was at 120. So that was my graph. This would have been words. This was time. That was in days. So there's my graph if we want that graph. Okay, now let's go to part D. Our last part, it says find W of 7 and W prime of 7. Well, W of 7, we plug it in. Now, it would have been nice for them to give us one of the ones we'd already done, but they didn't. But I still have it in my calculator, so I'll just change the 20 that I had in there to a 7. And I get 83.55, so we'll round it up to 84 words. And again, what that means, after 7 days, 84 words are still retained. And notice that's not great. He started with 120. A week later, he's only got 84 that he's retained. Then it says, what's W prime of 7? So I can't move that up too much because we need to take the derivative. So let's see. W prime of T. Oops, I already lost it. Now notice the 35 goes to 0. The 85 e to the power all stays. E to the negative 0.08 t. But then times negative 0.08. Now, that negative is why the derivative is negative, which we said because the graph's going down. And think about it, if we took the derivative again for the second derivative, we'd get times another negative, which would make it positive, which is why we have a concave up graph, because the second derivative is going to be positive. Okay, so we've got that. Again, I'm not, well, that 85 times 0.08 is not going to be a big deal, is it? 85 times negative 0.08. If you want to multiply those together, you can. This one comes out nice, but my caution is if it doesn't come out nice, don't round at this point. So this comes out nice. It's exactly negative 6.8. That's the 85 times the 0.08, the negative 0.08. Again, I'm going to erase those. Okay, so it's negative 0.68 e to the negative 0.08 t. And so now I can figure out W prime of 7 by just plugging that in, negative 6.8 e to the negative 0.08 times 7. And I get, let's see, negative 6.8 e to the negative 0.08 times 7, negative 3.88, or about negative 4 words per day. Notice this is a rate of change. So it's not just in words, but it's words per day. And it's specifically talking about the next day. Well, we're at day 7. So it's specifically talking about day 8. In day 8, the student we'll say this way, the student's words retained will decrease, since it's negative, by about 4 words. And we don't have to say words per day because it's in day 8. We're talking about which day that is. And remember, it's just talking about the next day, because if I did W prime, here I'll just plug one in real quick. If I did W prime of 20, I get negative 1.4, so about negative 1. So in day 20 to 21, in day 21, they'll forget about one more word. So we have to be specific about what day we're talking about. But anyway, there's some applications of that. We're going to see more applications of these a little bit later. So exponential is a nice way to set up. If something grows continually or shrinks continually, we can use exponential functions for that. But anyway, that's the end of that section. Hopefully that helps practice some of these derivatives, and they're pretty straightforward. Again, e to the x is the only function other than 0 whose derivative is itself, and then just remember the chain rule. All right, well, best of luck to you, and do your homework, and always ask if you have questions.